Now we're going to briefly talk about bomb calorimeters. You've already had a description of calorimetry and they showed you both types. Now, we're not going to use a bomb calorimeter. We just don't have the money to afford one. But we're going to show you how to do simple calculations with them. And here's a diagram of one. The bomb itself is that metal vessel in the middle. And basically what it does is it holds our sample, which is going to explode inside the vessel. And all the heat from the sample is going to go onto the water and all the rest of the surroundings. And just like a regular calorimeter, we're going to measure the temperature change, and to keep hot spots or cold spots from forming in the water, we're going to stir the water around a little bit. Other parts, well, you're going to put pure oxygen and our sample in the bomb, and to get it to catch on fire, we have to have a fuse. And so you see those two wires. Those are basically to fire off the fuse. Okay, so why are we showing you this if we're not going to actually do one in the lab? Well, because we're going to do calculations with them. Now remember, bomb calorimetry was not invented to be one more thing to vex chemistry students with. They are a practical, useful way of measuring enthalpy changes for things that won't work in a simple calorimeter. Generally, you're going to burn something. So the formula for a bomb calorimeter is remarkably simple. So we're finding delta H. All right. To do that, we're going to have something. Now, this looks like a little c. It isn't. It's a capital C times the temperature change. Now, I put in the negative sign. Nobody else does. And we'll show you why it's kind of annoying to put the negative sign in. So this is the difference. And this is the heat capacity, not specific, but heat capacity of the calorimeter. And it is not a specific heat capacity, though obviously it's closely related. The units are completely different. It's kilojoules per degree Celsius. Remember, a specific heat capacity was joules per gram degree Celsius, and it's specific for a certain kind of material. So what they do with the heat capacity of the calorimeter is that people who design the calorimeter take all the parts of the calorimeter, mostly the water, but also the bomb, the vessel, and the stirrer, and anything that can absorb heat. And they put those all together into one big heat capacity called capital C. You look it up when you use the calorimeter, and you use it in your calculations. So basically, they give you the capital C, you measure the delta T, and you get your answer. Now, let me show you one of the main places where they use these calorimeters. This might surprise you, I don't know. You've probably seen these before, and if not, you'll see them next time. They're on all commercially prepared foods you buy in the store, and it has all kinds of information about what is or isn't in the food. And the key one we're going to look at is the calories, which is the energy content in the food. Now, food is our primary source of energy, and we get energy from three things typically in food. There are fats. They give it a fancy word. They're sometimes called lipids, but they're fats. There are carbohydrates. And finally, there are proteins. Now, I'm writing them in this order specifically because fats have the largest amount of energy, and carbohydrates in the middle, and the proteins the littlest. But they're all sources of energy that our body takes in from our food. It's a rather complicated procedure because our body cannot use them directly. It has to convert them all to glucose, which then is transported to our cells. And within our cells, the glucose is combined with oxygen, and it's burned, believe it or not. and the heat from, or the energy, I should avoid the word heat because it's not always heat, is then used in our body to make, keep our body temperature up, to get our basic metabolism functioning, our heart and all that stuff. Take bio if you want to know the details. Okay, but you'll notice something. There are 3 different compounds. Oh, there aren't, because fats are a group of compounds, so are carbohydrates and proteins. Within each group, there are thousands of different types of fats, carbohydrates, and proteins. Every food has a different combination of them, but so they're not a single compound. And so it's impossible to do a molar enthalpy for food. What's a mole of bread look like? It's not a single compound. What's a mole of steak look like? Now, again, it's a complex mix of many different compounds. But that number, 230 in this case, calories, what's with calories? Well, remember the caloric theory? This is one of the last pieces left over from the caloric theory. It's an old unit of measuring energy, calories. Most of the world has switched over to joules or kilojoules. Yeah, okay, this is one of the few holdouts. And wait a minute, based on everything I've taught you, I thought those are supposed to be negative numbers. After all, it is an exothermic reaction, isn't it? Well, yeah, it is. Shouldn't it be negative 230? Well, hang on. This is for lay people, right? Not chemists, not physicists. If you started telling everybody there was negative 230 calories in 1 serving of whatever this is, they would think, oh, negative calories. It'll reduce my weight. They'll actually do the opposite. So it's exothermic, but they drop the sign. What they do to get these is they burn a sample of the food in a bomb calorimeter. So let's do a quick calculation of one of these questions. Watch closely. It's easy, but it's got a few tricks. So this is what I made up. I was being very vague, by the way. I don't know what kind of food I was thinking about. And let's see. Before I go running off in all directions, it's kind of important to know how I want the answer. It's not kilojoules, it's kilojoules per gram. So I'm going to need this. Now it's a very tiny sample because bomb calorimeters aren't that big. Okay, this would be that big C. And there's my delta T, and it's positive. So I'm looking for delta H. All right. I'm going to drop the negative sign because we don't care. Is big C delta T. Now I want it per gram. So I'm going to divide that by the mass. So I'm going to adapt my formula slightly. From here on, it's just a matter of putting the right numbers in the right spots. And you can use the units. Or I could go back and reread the previous notes. This is kilojoules per degree C. All right, that'll give me my kilojoules. Okay, this is my degrees Celsius, and they cancel with that. Now I want kilojoules per gram. Well, that's no problem. It's 0.100 gram. This is very easy. Go ahead and do it. Now, I would suggest you pause and then look at the answer, but this is the answer. That was very easy. There's not a lot of these questions, but they're easy marks. And if you want to be clever, it's negative 17.5 kilojoules per gram. But again, don't tell people that. They'll get very confused.